Okay. Okay, so I'm hoping, I really hope, it didn't work out last period, but I'm kind of hoping that you guys can have, it'd be nice to have a little time to actually go to the lab today. I'm hoping we can. We'll see how it goes. Let's take a quick look at the topics in 6.2 that we talked about before we left. Primarily what we had said was we want to be able to quickly and easily evaluate polynomials rather than having to just plug numbers in for x each time and make this big calculation. We had sort of a shortcut for that, right? Synthetic substitution. You remember how that went? Actually, and before we do that, maybe let's just review polynomials real quick. What's the degree of that polynomial that I've written down? 4. Good. How come?
4.
Okay, because that's the biggest power of x. Good. What's the leading coefficient? 2. Good. What is the constant?
X.
0. Who said that? Good. Why is it 0?
Because there's no value for x to the 0.
Okay, good. So remember, the constant is the number that appears, it's the coefficient of x to the 0, which we don't write. Anything to the 0 power is always equal to what? So like 1,975,493.97543 to the 0 is 1. Anything to the 0 is always equal to 1. So x to the 0 equals 1. So we never write it. We just write the constant by itself. But the constant therefore is the number that doesn't appear as a coefficient of x at all. It's just a number. Do you see that one up there? There isn't like a +3 or a -11 in this case. There isn't any number by itself, so what must it be? 0. Because we wouldn't write it then, right? We don't write +0 at the end of something. It's just implied. So the constant would be 0. Is that polynomial in standard form? Yeah, I see people nodding their heads. Yes, it is. It's in all the exponents are decreasing in value as I go from left to right? So it works. Now, when I do my synthetic substitution, which really we'll find out is actually even trickier than that. It's really synthetic division, but we just haven't gotten to that part yet. I'll get you started. Remember how that works. We always start with our bracket. Okay, now what are the numbers that we write in the bracket, in the top part of the bracket?
2, 1, -3, 5.
2, 1, -3, 5. Is that it? And 0. We have to have a coefficient there for every power of x, including the constant. And to make sure we never mess that up, we can always kind of do a quick little check here. We know that if this is a 4th degree polynomial, how many numbers am I going to have to write down, guaranteed? 5. I always have to write down 1 for each power of x plus the constant, right? So it's always going to be 1 more than the degree of the polynomial. Now, one last thing I want you to do. Remember, we want to put that box, the answer box, under the last number. Okay, now what? If we're trying to do this, right, we're trying to find what is f of -1. In other words, we're trying to find out what is the value of the function when x equals -1, right? That's the number we're plugging in for x. So now what do I do with that -1? Okay, put it out front. Whatever the value of x that we're substituting, that goes out front, right? And now we're ready to do the whole synthetic process. So how do we kick that process off here? Yeah, okay, I'm hearing it. We drop, the first number just gets dropped straight down, and we have a rule. Whenever a new number appears below the bracket, what do we always do? Multiply by... Okay, the negative, whatever the number is out front, in this case, -1. So -1 times 2 is -2, and we're just going to push that up diagonally into the next column. And then we just add in each column. So 1 plus -2 is -1. Good. Okay. -1, we got a new number, so I multiply. -1 times -1 is +1. -3 plus 1. New number appears, -2 times -1. And we don't need to write the arrows, but I'm just for now. 5 plus 2. Okay, so what goes here then? And then when I add, what do I get for my answer? 7. About that. Okay. Now, of course, we could do this by just brute force, by just plugging in that value, that number, that's that value of x, plugging it in for x, and just and doing that all the way through. But those can be pretty big numbers. This is an easier way to do it. There is a shortcut on our calculators too, though, right? Remember, I want you to be aware of this because this is a good one. Okay, remember what we can do here. Oh, that's not good. Smart. Okay, if I want to evaluate a big function, doesn't even have to be a polynomial, on my calculator, all I have to do is I want to store this x value as the variable x. Remember how we do that? That's it. Good. So I'm going to take the number -1, and I'm going to store it as x. And if I hit enter, then it just tells me -1. So now that's stuck in the x value in the calculator is now stuck as -1. So all I have to do now is just type in this expression and hit enter, and every place I have an x, it's going to replace it with -1. Okay, so 2x to the 4th plus x cubed minus 3x squared plus 5x. And if I hit enter, look what we get. There's our -7, right? Now the nice thing about this, and they do this a lot on standardized tests, is now if they want you to, like a lot of times on tests, they'll do things, you probably saw this on the Oaks, for example, they'll give you multiple choice answers. They'll say stuff like, the value of this function at x equals -1 is, and they'll give you, 4 or 5 or 6 choices, and you got to pick the right one. If it's a really complicated function, unlike a polynomial, maybe that's hard to figure out. But all you have to do on a calculator, once you've entered the expression, is I can just keep going back and plugging in new values of x and evaluating. So once I get this expression in there, that's half the battle. What if I wanted to evaluate this at, say, x equals 25? I could just store 25 as x, and then just go back up and grab this expression and hit enter, and there's the value of the expression when x is 25. I can do that as many times as I want to. Yeah. Okay. So that's a handy way to do that on a calculator. Okay, so that's evaluation stuff. Let's move on. What if we look at this about? Okay, the one topic we didn't really get to was end behavior. And let me explain what this means. When we want to analyze a function, a lot of times we don't really need an exact graph. A lot of times we just want to know certain things about that function. One of the things we might want to know is, what does it do out at its ends or its tails? In other words, if an ant were to walk along the function infinitely far to the right, what's that? What kind of behavior is that ant going to experience? And a lot of times things will happen, like maybe that ant will start to run into a horizontal asymptote. Maybe his y value will approach a certain constant value, and then he just walks along a horizontal surface the whole way. It might be that the ant just wiggles around forever, like on a sine function. If that's the case, we want to know that stuff. But usually, and in the case of polynomials, something different always happens. In the case of polynomials, there's one of two things that will always happen. We don't know what's going to happen in the middle. That can be complicated. There can be all kinds of peaks and valleys and all kinds of crazy stuff going on somewhere in the middle of the function. But on the tails of the function, if I go really far to the left or really far to the right, there's only two possibilities for a polynomial. Either, when I go to the left forever, either the y values are going to get infinitely large, so the ant is going to climb up an infinite hill, or the y values are going to get infinitely negative, and the ant is going to walk down an infinite slope. One of those two things always happens. Same thing at the right. If the ant walks to the right forever, he's ultimately either going to climb up an infinite slope or he's going to walk down an infinite slope. One of the two, guaranteed. We just want to know which one. which one of those things is happening. Now, the way we talk about this in math, a lot of times we want to talk about limits. And we're not going to really get into too much in the way of limits this year. That's more of a next year topic. But we can at least mention that word now. So when we say things like this, as x approaches infinity, positive infinity, isn't that really kind of a math way of saying that the ant is going to walk forever to the right? I mean, because if he's approaching infinity, of course he's never going to get there, but that leaves a lot of wiggle room for us. It just says there's, we can have him go as far as we want to. There's no bound to it. No matter how far he goes, if he just keeps on going out there, what kind of functional behavior is he, what kind of terrain is he going to climb? Or is he going to see when he gets there? Is he going to be going up or down eventually? So that's kind of our math way of doing that. We'd say something like x approaches, as x approaches, and we use an arrow for that. As x approaches positive infinity, f of x was just a fancy way of saying y is going to do what? One of two things is always going to happen. Either f of x is going to approach positive infinity if he's climbing up a slope, or it's going to approach negative infinity if he's climbing down a slope as he goes to the right. Make sense? Okay?
Why is it so hot in here?
You know, because this thing is broken. It just, I cannot get this
I
thing.
feel like
to-
I'm in Vietnam.
Maybe. I don't know. But I'll try. Hopefully that'll work.
That's what I
And the same thing is going to be true as x approaches negative infinity. Hey, Boozer, you better put that away. That's going to be nothing but trouble. Okay, as x approaches negative infinity, that's our math way of saying as the ant walks forever to the left without bound, then also one of two things is going to happen. And our goal is just to figure out which of those two things. We always know that with infinite x behavior, meaning as I go forever to the left or right, we know the result, the vertical result, the y result, is always going to be some kind of infinity. The slope is always unending. It's always infinite. It's just a matter of, is he climbing up or down with that infinite slope, right? So whenever we do questions like this, we know most of the answer already. The question that you're going to do on Moodle, for example, would look something like this. As x approaches negative infinity, for some function that you're given, f of x approaches, you already know that there's going to be an infinity there. The question is just, what is the sign going to be? Is it positive or negative? That's all you're figuring out all the time. Is it an uphill or a downhill that he's dealing with? Okay? All right. So, how do we deal with that stuff? Well, let's take an example of this weird polynomial. Okay, and let's just look at its graph. This is kind of a bizarre polynomial, but it is just a polynomial, isn't it? It fits all the criteria. Look, I've got three terms. Each term is just a number times a power of x. The powers of x are whole numbers, and the coefficients don't have i's in them. They're real numbers. So that is a polynomial. Now, if an ant walks infinitely far to the right or the left, what do you think, which part of that polynomial do you think is going to matter the most? When I say which part, I guess I mean which term. The x, okay? And because, and I can see the reasoning for that, because these are such tiny numbers that they're going to make those ones really small, aren't they? Right? Let's just take a look and see if does that make sense? Okay, let's explore this a little bit and see what we get. So if I pull up my calculator, and I just happen to already have that function in here, what are the odds of that, right? It's all in there. Let's set our window this time to go from like -1 to +1. And we'll just go zoom fit. And that's what we get. What's that look like? What part of that function does that look like? Y equals 0.0001 x cubed, y equals 0.01 x squared or y equals x? Y equals x. Stands to reason because those decimal points made these contributions very small, so this was the part that mattered the most, right? But watch what happens as x gets bigger. Okay, and I want you to think about something as we look at these graphs. These coefficients are constant. They're pinned down. They're not going to change, are they? But as we pick bigger and bigger values of x, the contributions of the x and the x squared and the x cubed are going to change accordingly, right? Think about, for example, just the number 10. 10. If x equals 10, then x is 10. What's x squared going to be? 100, right? 10 squared, if x is 10. X cubed is going to be 1,000. That's quite a bit bigger, right? And as x gets bigger and bigger and bigger, that disparity is only going to grow. When x is really small, if x is 1.1, then 1.1 squared is not very much bigger than 1.1. 1.1 cubed is barely bigger than that. There's not much of a change. But as x gets really large, the difference between those terms is going to grow. Let's take, for example, what if we let our window go from, like negative 120 to positive 60, for example. I go zoom 0. Oh, what's that look like? That looks an awful lot like a parabola, doesn't it? Yeah. Right? Now, which part of this function would give the graph of a parabola? The squared would, wouldn't it? Right? Remember back from chapter 5, we know that the graphs of quadratic functions, which are x squared functions, are the ones that give us parabolas, right? Does that make sense? So this guy's looking an awful lot like a parabola now. Okay, but if I even go further out there, if I go out there, let's make this guy go out, let's say this time, let's not mess around, let's go from like negative 10,000 to positive 10,000 on the x scale. Okay, any predictions? Any predictions about which part of this function is going to dominate now? Yeah, the x cubed part. You'll see, it will for sure, because 10,000 cubed, wow, 10,000 cubed is going to be an immense number. 10,000 squared is pretty big, but 10,000 cubed is how many times bigger than 10,000 squared? 10,000, yeah. It's going to be 10,000 times bigger. That's pretty large. On this little puny screen, you're not even going to be able to see those kinds of differences, right? So if I go zoom 0, so the calculator kind of fits the y's for me, now that does not look like a parabola anymore. That looks like, and you'll get to see this too, as we talk more and more about what different kinds of polynomials look like, you'll recognize immediately that looks like a cubic polynomial. That looks like an x cubed function. In fact, if I graph that next to, watch this, if I graph that next to x cubed, well, x cubed is going to be a lot bigger because this is multiplied by that very small number. But if I graph this right next to, how about if I do this? Just to demonstrate something, this would be kind of cool. If I graph this right next to just this first term by itself, you'll see how there's not much difference. So 0, so y2 I'm going to graph is 0.0000 x cubed. Okay? Oh, sorry, need a 1 in there, don't I?
Yeah.
Well, I'm hoping. Yeah. Okay, so let's try this. So now graph, there's the first one, and there's the second one.
Right on top of it.
There's not much difference, right? You can see maybe a little bit in there, but once it gets out there further, there's virtually no difference. So that demonstrates pretty clearly that that first term is the dominant one, right? Okay, so, all right, so what about that then? This is, to me, this is kind of, you'll come back to this again and again. I think having seen that, though, that'll help. In math, then, when we're dealing with a polynomial like this, we always say that the leading term, or the first term, in math, we actually call that the dominant term. That's the dominant term because when we're considering the end behavior of the function, as x is approaching negative infinity or positive infinity, in other words, huge, huge, huge values, the only one that's going to matter is that first term. The other ones are just dwarfed. We don't even care. We don't even have to worry about them. We just know that this is the one that matters, right? And so if I want to answer the question for this function, as x approaches, for example, positive infinity, f of x approaches what kind of infinity, it's pretty easy to tell, right? All we have to do is look at that first term. That first term is going to give us what sign, if x is approaching a positive value, right? X is positive. A positive number, positive value of x cubed is what sign? Positive number cubed is positive. Times a positive number out front. That's a positive 0.00001. Positive number times positive number gives us back a result of positive. So it's positive infinity, right? What about as x approaches negative infinity? F of x approaches what flavor of infinity, positive or negative? Once again, just look at the first term. Look at what the result is going to be. That dominant term, I'm going to get a sign of positive, which is this part right here, the coefficient, times what about the x cubed part? As x approaches negative infinity, x is negative. What is a negative number to an odd power always going to give us back? Negative. So I'm going to get positive times negative, and what's the result of a positive times a negative? Negative. See how that works? So it's negative infinity, guaranteed.
So you have to find the dominant term first to be able to do that?
Right,
or
but
is it just the first term?
Right, in a polynomial that's easy because if it's written in standard form, it's just the first term. So all you have to worry about is just the behavior of the first term.
If it's not in standard, can you just make it in standard? And
Right,
then
right,
still the first
right.
term?
Because we'd always like to have a polynomial written in standard form anyway. So what about this guy? We can keep going with that. What about this one? What about this one? What our function is f of x equals negative 5x squared. As x approaches negative infinity, f of x is going to approach what? Well, we can find out. F of x is going to approach some kind of infinity, right? What's the flavor going to be of infinity, positive or negative? Well, let's see what we get. Aren't I going to? Okay, listen. I want everybody with me here. This is something. If you get this, people sometimes have trouble with this, but if you just really focus, you'll never forget this. You'll have this forever.
Gotcha.
So f of x approaches. Well, we know we're going to get, positive or negative times positive or negative, whatever that's going to give us, infinity, right? So what's the negative 5 is negative, right? Now what about this part? If I'm putting a negative number into x squared, a negative number to an even power is always positive. So I'm going to do a negative times a positive. Negative times positive is negative. It's negative infinity, right? Okay, now you can look at that if you want to. You can, how am I going to do that? Anyway, let me just erase it. So you can also look at it this way. That's the easiest way. If you want to, you could even treat the infinity like a number. Take your pick. You see, look what I've done here. If I literally plug in negative infinity in for x, this is the result I get. Well, negative 5 times negative infinity squared. Now, does that make any sense? You can't really do algebra with infinities, but the concept makes sense. If I have a really big negative number, call it negative infinity, just means a really big negative number, and I square that, aren't I just going to get back a really big positive number? Right? So isn't this literally kind of, you can think of it as being equal to negative 5 times positive infinity? And a negative number times a really, really big positive number is a big negative number, right? So you could even just do the algebra with the infinities if you want to. But I think it's probably easier just to do it the way I was showing. What about this guy down here? Let's look at this one and then we'll move on. So what about this one? As x approaches positive infinity, what are we going to get? Well, we're going to get -5. The coefficient's always just negative in this case. A positive number, if I take x equals positive infinity and I plug that in for x, a positive number to an even power is positive. In fact, a positive number to any power is positive, right? And so I get negative times positive equals negative infinity, right? Make sense? Okay, and if you want to, you could just, you could just think of it as plugging positive infinity in. -5 times positive infinity squared is like taking -5 times positive infinity, which is like negative infinity. Take your pick. Okay? Make sense? Okay? If you can do this one, I'm convinced. I won't even show you the tables and we'll be done. So talk me through this one. As x approaches negative infinity, what's f of x going to approach? We need to get the sign. So the coefficient is positive, so that 3 is positive. If I'm putting a negative number into x cubed, a negative number to an odd power is negative, right? Negative number to an even power is positive. Negative number to an odd power is negative. So this one's going to give us negative. And so the result then is positive times negative is negative infinity, right? Okay, what about down here? As x approaches positive infinity?
Positive everything.
Yeah, I'm going to get positive. A positive number to any power is positive, right? We good?
Yeah.
Okay. All right, I'll get a little time. Let's go to 205.